We introduce a benchmark providing shared hardware for evaluation, which we call train offline, test online, or TOTO. In the TOTO framework, we provide a real-world dataset collected on our hardware. Remote users train offline policies of their choosing on this data, and they submit these policies for evaluation on our real-world setup. The evaluation results guide their future iterations of development. And finally, these evaluations form a leaderboard, giving direct comparison on shared tasks, data, and hardware. Our training dataset consists of two tasks, pouring and scooping. Here we show representative trajectories with varied objects, materials, lighting, and target locations. The initial release contains 2,000 scooping trajectories and 1,000 pouring trajectories. The first question we address with TOTO is, what makes a good visual representation for robot learning? To answer this, we train behavior cloning policies on top of frozen representations. We evaluate these policies on our shared hardware, and the results inform us about which representations work better. We evaluate 5 such visual representations, each contributed by remote users. We have 2 that are trained on our dataset, BYOL and MoCo, and we call these in-domain. These are in contrast with the more generic ones, MoCo and ResNet 50 trained on ImageNet, and R3M trained on Ego40. Here we show evaluations of BC with each representation. The best performing ones are the 2 in-domain models on the left. Pouring requires more location precision than scooping. All methods see a small performance drop moving from train object locations to unseen test locations. We also ask, what's a good method for offline policy learning? Remote users contribute 4 initial methods: behavior cloning on successful trajectories, VIN, which selects actions using nearest neighbors, IQL, which is an offline RL method, and decision transformers, which recasts offline RL as a sequence modeling task. Here we evaluate these policy learning methods on scooping. VIN and BC perform the best. And VIN sees the biggest drop between train and test, which makes sense since it selects actions according to the training dataset. DT is unable to solve the pouring task in either train or test locations. BC and IQL both see success on test locations, but still experience a significant performance drop. We're soliciting additional baselines, so submit your favorite vision representation or policy learning method today. To learn how, please see our website, which includes dataset and code details. Thanks.